All right, so we're now going to go ahead and derive the current divider equation so that anytime you see a circuit in this configuration, you can go ahead and use it. This one's a lot less common than the voltage divider, but it's necessary to cover just because it's so similar, and it'll probably show up somewhere, and then you'll be happy that you learned it. So I'm going to go ahead and call this source I source. And I'm going to call this current I1. I'm going to call this current IT, kind of for I total, because again, the sum of the current entering is equal to the sum of the current leaving. And then I will call this current I2. And I'll call this resistor R1, and I'll call this one R2. And then I'll let this voltage on this node up here be equal to Vx. Of course, this voltage down here is 0, but we should very well know that by now. So the first thing I can notice is that these two resistors are, of course, in parallel, and they have the same voltage across them, Vx minus 0, which is just Vx. That's going to be equal to I times R for the first resistor, and it's also equal to I times R for the second resistor. Okay, so that's the first equation that we're going to use here. The second equation we're going to use is KCL at this node. And so what I can write from KCL is that sum of the currents entering, which is IT, is equal to the sum of the currents leaving, which is I1 plus I2. And maybe it's not super clear to you yet that I2 is leaving that node, but it definitely is. It flows just like this out of that node. So hopefully that's clear. And so I have these two equations. What I can do is I can sort of rearrange this one, and I can say that maybe I'll just solve for I1 is going to be I2 times R2 over R1, just by dividing both sides by R1. And now I can plug that into my equation here. I can say I2 times R2 over R1. Oh, I accidentally selected the thicker marker. I was wondering why it looks so thick. Let me just undo some of this. So IT is, now I'm plugging in for I1. It's going to be I2 times R2 over R1. And we remember correctly that what we were trying to solve for in the previous case were the currents, I2 and I3. This time I have them labeled I1 and I2, but it's the same thing. We're trying to find these. And so this current divider method is going to give us an equation which allows us to solve for those directly without having to actually combine the resistors in parallel. Okay, so I've got this expression here. I can basically extract I2 out or factor it out to where I'm left with just this. And now I want to solve for I2 in terms of IT. So I will divide both sides by this entire term here. And I'll get that I2 is IT times 1 over R2 over R1 plus 1. And now I can multiply the top and the bottom by R1. And I will get that I2 is equal to IT times R1 over R2 plus R1. All right, so that is the current divider equation. So basically that's telling me if I want to solve for the current I2, let me get my laser pointer. I want to solve for the current I2, I take resistor 1, so the opposite resistor, divided by the sum of the two resistors and multiply that by my total current. So it's sort of opposite. It's interesting that the resistor that, I mean, I guess you would hope that for memory's sake, the resistor on the numerator would be the one that's actually associated with the current that you're trying to find, but it happens to be the opposite. And so if I were to go through the same derivation for I1, I would basically get that I1 is I total, multiplied by R2 divided by R2 plus R1. And so that is the current divider equation. And now anytime you see anything in this configuration, I guess I'm on my arrow tool too. If you see anything in the configuration where you have a current source and two resistors in parallel, then you know this current. You can solve for these currents using these two equations. All right, so we're done with the current divider, we're done with the voltage divider, and we are ready to move on to the last section of this module, which is learning about dependent sources.